Hello everyone. In this video we discuss Rayleigh power method. Rayleigh power method is an iterative method and it is useful to find the dominant eigenvalue and the dominant eigenvector of a matrix. Firstly, let us define dominant eigenvalue and dominant eigenvector. Let us consider n cross n matrix and let lambda 1, lambda 2, lambda 3 and so on lambda n be eigenvalues of this matrix A. Then lambda 1 is called the dominant eigenvalue of A if absolute value of lambda 1 is strictly greater than absolute value of lambda I, where I is equal to 2, 3, 4 and so on n. The eigenvectors corresponding to lambda 1 is called dominant eigenvectors of A. For example, now if I consider this matrix, A is equal to minus 5, 4, 2, 0, 3, 1, 0, 0, 3 again. Look at this is upper triangular matrix. From this it's clear that eigenvalues are minus 5, 3 and 3 are diagonal entries. The three eigenvalues, it's clear that absolute value of 5 is greater than all the other eigenvalues. From this we can say that 5 is a dominant eigenvalue. And the corresponding eigenvector is a dominant eigenvector. Now let's consider this example. 7, 0, 0. Let me consider a diagonal matrix. 0, minus 7, 0, 0, 0, 3. Now in this example, there are three eigenvalues. One is 7. Let me call this lambda 1. Lambda 2 is minus 7. And lambda 3 is 3. If you see this carefully, there is no dominant eigenvalue of this for this matrix because if I consider the absolute value of 7, this is not strictly greater than absolute value of minus 7. Because the 7 is equal to 7, we cannot say that this is strictly greater than this. Thus, this is not strictly greater than minus 7, absolute value of minus 7. Therefore, it has no dominant eigenvalue. And note that not all matrices has a dominant eigenvalue and eigenvector. Now let's see an algorithm to find dominant eigenvalue and eigenvector. The method is called power method or Rayleigh power method. Let us consider an enclosing matrix. Let's assume that capital X, this is the dominant eigenvector. To find this, first we start with this by considering non-zero vector x naught. This is something like initial guess to the eigenvector, dominant eigenvector. Using x naught, we construct sequence of vectors x1, x2, and so on, xk plus 1, and so on. Okay, and this sequence of vectors approaches to the dominant eigenvector x. Now, our task is to see how to find this x1, x2, and so on. To find x1, what we do here is we multiply a and x naught. Now we get a column vector and identify the numerically largest entry in this column vector. Once identified that, you can write this column vector as this scalar, that is lambda 1, that is numerically largest entry in this column vector. You can take that, extract that outside the column vector into, we get another column vector. And this is first approximation to the dominant eigenvalue, and this is a first approximation to the dominant eigenvector. Now, in general, if xk is obtained, then the vector xk plus 1 is found by considering this product axk and writing this as a lambda k plus 1 and xk plus 1, where lambda k plus 1 is the numerically largest entry in this column vector axk. And this is a k plus 1th approximation to dominant eigenvalue, and this is a k plus 1th approximation to the dominant eigenvector. When to stop these iterations, and what we do here is we find the difference of these two vectors. If difference is less than tolerance, here we assume the tolerance is 10 to the power of minus 4. If that is less than 10 to the power of minus 4, then we stop the process or stop the iteration. Here I considered L infinity norm, which is defined here. The L infinity norm of this column vector is a maximum of the entry in the column vector. That is the maximum component in the column vector. That is, we find this difference if we find the difference and the corresponding entries will be subtracted, and each and every entry must be in this difference must be less than 10 to the power of minus 4, then we stop the process. Actually, this is like absolute value of xi. Now let's see an example to find the dominant eigenvalue or dominant eigenvector. First, let's consider non-zero vector as an initial approximation to the dominant eigenvalue. Let me start with this initial approximation, x naught. Now, to find this first approximation to the dominant eigenvector, we multiply this a and x naught, which is equal to 5412 multiplied with 10, and we get 51. Look at this, there are two entries in this column vector, and the numerically largest entry is 5. Therefore, we can write this vector as 5 times 1, and second entry will be 1 divided by 5, which is 0.2. Now we call this lambda 1. It is a first approximation to the dominant eigenvalue into x1. Okay. Now to find this second approximation or second approximation, we multiply a with x1. 42 and x1 is 0.2. Once we multiply this, we get this one 5.8, 1.4. And obviously, numerically largest entry in this column vector is 5.8. Therefore, we can write this as 5.8 into 1. And second entry will be 1.4 divided by 5.8. It is 0.241. Let me call this as a lambda 2 and x2, which is a second approximation to the dominant eigenvalue and eigenvector. Now to find lambda 3x3, we consider this product 5412, and this is 0.241. After multiplying this, we get this one. Okay, let me write this directly. We get this 5.966 into 0.248. Let me call this as lambda 3 and into x3. Now we repeat this process till we get desired accuracy, the solution with desired accuracy. Here let me consider the tolerance as or if it is approaching to some number, we stop the process. Let's do a few more iterations. A x3. Yeah, we are multiplying this to find a fourth approximation, a fourth iterative value. 5412. This is 1 0.248. this is approximately 5.994, 0.25. This is a fourth approximation, right? Earlier we found third approximation, this fourth approximation. Let me call this lambda 4 x4. Now we repeat this process. You can see that ax4, if you multiply this to a times x4, we may get this 5.999 and 0.25 again, lambda 5 x5. And if I multiply this again, you can say that this will be approaching 6. Let me write this 6 itself as a sixth approximate value. Look at this. We repeat this iteration until we understand that this is approaching some number, some integer or some standard number, which is known. Otherwise, we find a difference, as I said here. If this difference is less than tolerance, we stop the process. Now we stop the process, then we can say that after 6 iteration, dominant eigenvalue of A is 6 and dominant eigenvector of A is this 0.25. That's it. Now we stop here. And before we stop, let me say you something. No, in this case we have to consider numerically largest entry. Even though if it is a -1, -5, 1, for instance, in this case numerically largest is 5. Therefore, we can consider this as 5 times. Okay, you can take this 5 outside, -1 by 5. Okay, you can proceed in this way. Okay. With this note, let me stop this video.